seed to come through and actually form it. Okay, so why are they warming? When people think about global warming, they usually think about greenhouse gases and CO2, but the vast majority of the Earth's energy balance is not actually determined by that. It's determined by things like clouds. And so how do clouds, how does it work? Okay, so during the day, you get sun shining on the top of the cloud, and they're white, so they reflect a lot of light back into space. This has the effect of cooling the Earth, essentially. And if you have no clouds, the sun will hit the ground and it will get absorbed and it'll produce heat. And then as the Earth warms up, just like a fire or something else, it glows in the infrared and it emits infrared light back into space. And the sun and the Earth have to be in equilibrium with each other. Otherwise, the Earth will heat up until it gets to the point where it starts emitting enough thermal light to balance out the sun. Greenhouse gases change that equilibrium, which is why they're called greenhouse gases. But clouds do the same thing. And so a cirrus cloud from an airplane, this is an example at night where you have no sun, will essentially scatter infrared light back to Earth or absorb it in the atmosphere. And they're very cold. So from the top of the cirrus cloud to space, it emits very little infrared radiation. And so this effectively traps heat, kind of like putting a scarf around the Earth. And here's an example of what that looks like. So on the left-hand side, you can see sort of the shortwave cirrus. You can see two cirrus. This is the same image, actually. So on the left, you can see what it looks like in the visible. And I've circled a cirrus cloud. You can see how it's reflecting sunlight back into space. On the right side, you can see what it looks like in the infrared. It looks dark because it's blocking all the heat that would otherwise go to space. And so cirrus clouds are actually part of the natural balance of the Earth. They cover about 20% of the Earth on average. And contrails increase that from 20% to like 22, 24%. Basically, they increase the cirrus cloud coverage of the Earth significantly, and cirrus clouds are a huge driver of warming. Okay. For those of you that are following online or in here with laptops, you're welcome to go to this. This is a demo that we've set up where you can actually see sort of the real-time view of contrails being made, at least at the moment in the Western Hemisphere, though we are currently expanding that out. You can also look at the amount of infrared light that's leaving the Earth and the amount of solar radiation that's being reflected and all the contrails that we've detected. It's also worth noting that not all contrails are the same. I talked about some being wider. At night, they can trap a lot more heat because they're relatively, because there's no sunlight being sort of reflected off of them to balance it out. And so when we went to airlines and we talked to airlines about it, we realized that actually they only really have to avoid a relatively small fraction of contrails in order to get the vast majority of the warming. And part of the project that we have is to figure out how to predict that ahead of time. Before I get into that, also, I wanted to show this. When people usually think about global warming, they think about things like CO2 that are well mixed over the whole planet. So the jet fuel leaving an airplane engine will eventually get mixed over the entire hemisphere and the rest of the world very quickly. Contrails, being such short-lived things, concentrate the heat in the areas of human, basically in the areas of air traffic, which highly correlate with human habitation. And so I particularly like to point out Europe here has an enormous amount of air traffic density. The estimate is that the radiative forcing from contrails, the extra cirrus clouds from contrails over Europe, contribute to roughly over 1 watt per square meter of extra heat in Europe. And as for reference, right now in 2025, the total radiative forcing balance from all of the rest of climate change is roughly like 1.5 watts per square meter. So this is a significant fraction of extra heat that's highly localized in those regions. And I was curious, so I was also looking at Australia before I came here, and you can kind of see the flight tracks for flights leaving. There's 2 little clusters for leaving Sydney and Melbourne. But basically for Australia, it represents roughly 10% of the global warming that's happening right over the city. Okay. So the goal of our project is to find ways of mitigating this. And so how can we do that? Well, it turns out that as I mentioned earlier, only a very small fraction of flights make the majority of warming. And if we can predict those locations where they will happen ahead of time, we can pass that information to the airlines before they fly through them and reroute around those areas. As a side note, I won't cover this too much, but we also do a bunch of climate modeling to understand things like seasonal averages, what time of day is worth doing avoidance for, and then also looking retrospectively to see which flights made contrails and which didn't, so we can update our predictive model to know whether or not, and to validate it, essentially, to know that we're doing a good job, and to look at different avoidance strategies. Okay, and then, so this is the kind of map that we can pass to an airline, and we can basically tell them like, oh, okay, the areas of blue are areas that you can go through, the areas of white are areas that you're not gonna make a contrail, and the areas that are red here are areas where if you went through, you would make a contrail and it would be highly warming. And this is at all altitudes, so usually only a very small fraction of each individual altitude represents a contrail warming region. And as a result, airplanes can essentially route around those laterally or deviate vertically to avoid them. This is a study that was a couple of years old now, but I get to talk about it publicly. We've done other ones since then. We did this trial with American Airlines where pilots started out in Dallas and they would fly a route out and back, so say out to Seattle and back. And we would pick flights where the destination airport was going to make contrails on that day. And we randomly assigned flights to either avoiding contrails on the outward leg or avoiding contrails on the return leg to determine whether or not we could see the effect of trying to avoid contrails operationally. And this is the sort of a side view of a flight plan that a plane would make. So this is the plane sort of taking off, say, out of Seattle. I don't remember actually which airport we were at. And then this region here, this white region, is an area where we believe that contrails would be made. So the plane would sort of level off at 32,000 feet and avoid the contrail region before climbing to their final altitude of 38,000 feet and then descending back into the final airport. Whereas the original flight plan was to follow this gray line that would have gone straight through the contrail zone and then come back. And we did a lot of manual verification for this particular trial where we looked at where a contrail would be if a particular American flight made one. And then these blue areas are areas where we detected them. And we matched them up by hand. And we found that just with this simple avoidance scheme, we could reduce the amount of contrail warming in about half. And since 2023, we've started to integrate operationally into different airlines. So the airline market is a strange one, but every airline sort of has an operational software partner that they work with to do flight dispatching or planning exactly where they're going to fly. They'll take into account things like wind data. So if it's better to fly 1,000 feet higher or lower, depending on the efficiency of the engines and which way the wind is blowing. And now we add contrails as an extra constraint. Let's say can turn it on or off, or decide how much they're willing to try and avoid contrails, and do that in an automated way. And then in addition to that, we retrospectively look at the paths that everyone took, and we determine from satellite information how many contrails were made, and then we can pass that information on to regulators who, especially in Europe, have started to regulate contrail formation. Okay. Well, that was my last slide on contrails. I will be around a little bit afterward for people who have questions, but I'm going to skip ahead to the next part. Okay. Complete change of topic. Still, I actually didn't mention the total number up front. Contrails represent something like 700 megatons of CO2 per year. So if we can do contrail avoidance, that's roughly the equivalent of like 1% or a little bit over 1% of climate change, about the same as the country of Australia. Okay. So fires. We're moving on to fires. I know that 2019, 2020 left an impression for people, many people here, I imagine, for fires in Australia. The couple of years after that, the rest of the world were actually much worse. Especially in the boreal forests, areas where they're not well adapted for fire. You don't really see fires very often in Canada. There's some places there where their fire return interval might be hundreds of years long. And so it takes a very long time for forests to recover when that happens. But as the earth warms up and the climate shifts, we're starting to see a lot more fires. And we wanted to get ahead of this because while it was bad here, and it has been bad in other places, the projections are to have something much worse, unfortunately, over the next couple of decades. And so we had this idea that we should try to use technology to get ahead of this. How could we do that? We didn't know how to do that. We spent a long time thinking about it. This is one more graph, just kind of showing. This is for Western United States. I apologize. I had the same graph for Australia, but I lost it, and I was desperately trying to find it before I came. But there's a very similar curve, which is very sad. But essentially, you can see that the most recent years are clustered towards the top right, where it's sort of dry and warm. And in those years, you get a much higher amount of area burned. And this is part of like a longer term trend that we see almost everywhere in the Mediterranean climates. This is the last 50 years and the change in incidence of fire weather over the time. And you can see that, you can see sort of an effect in Australia where you get a higher incidence of fire. And in the Western United States, there are places like Sub-Saharan Africa which actually see a reduction. So it's not all the same direction. But this gives you a rough sense for how things are changing. Especially concerning are the areas here which are very high carbon boreal forests, and in Russia, and then this area of the Amazon. Okay. Fires represent an enormous amount of carbon flux, both in and out of the atmosphere. So when a fire burns, especially a crown fire can destroy the forest, it releases an enormous, it releases a bunch of chemicals, but it also releases a bunch of CO2 and black carbon into the air. It's roughly the equivalent of 11 gigatons per year of CO2, so roughly 20% of anthropogenic emissions. But forests will grow back, carbon will be reabsorbed. So it's very complicated to do the accounting for this, but you can roughly think about it right now with the trends that we have in climate. The net is about, I think we calculated about 6 gigatons per year. And it also, there's a lot of smoke, contributes to a lot of deaths worldwide, and there's an enormous amount of damage. So like Los Angeles in January, for example, had $105 billion in damage. It's a fun time for people in California. But globally, it's a very large number. An enormous amount of money is spent on fire management. So Australia spends a lot of money on fire management. The state of California spends a couple $2 billion a year on fire management. So we're trying to figure out how can we insert ourselves to help drive down the emissions while still sort of managing the forest properly. Now, I already talked a little bit about the trends in the boreal forest. Up and to the right is bad. I'll just skip over this, but okay. So the idea that we had, and we originally tested this out with loon balloons. I don't know if anyone remembers the loon balloons, but there was these stratospheric balloons that Google had that would fly around at 20 kilometers in the air. And we could attach cameras to them and take pictures of fire, and they looked great. There's a long story with that program, but that program shut down. And so we switched to this idea, which was that we could use novel dedicated satellites to detect fires in real time globally. And then we could use a bunch of machine learning to clean it up, because when you try to look for fires globally, you see everything, and it's hard to tell what's a fire and what's not. And then we could come up with a bunch of alerts, and we could share that with fire agencies. And the idea was that early detection and tracking of fires would allow fire agencies to have more time to respond to fires. And with more time, gives more management options. And you could potentially reduce the incidence of mega fire events, which were a hugely destructive ecologically, but also just free up resources so that they can respond to more fires, because the average fire they would get to will be smaller. Okay, before we spend a bunch of money on building satellites, we did some retrospective analysis with existing satellites to understand how often fires burn before somebody actually calls it in. I think you have 000 here in Australia. We have 911. So we looked at a bunch of 911 call logs for fires in the United States, and we put a timestamp on them. We said, okay, this is exactly when the fire was discovered. And we looked at all the satellite passes that we had within hours beforehand to understand, do fires burn for hours before somebody calls them in, or did they call in immediately? And over many, many fires, you can create some statistical samples for this. And so you can see, like for fires that are maybe many hours before the 911 call, it's very rare to see a fire in the satellite image, but once you get closer and closer in time, you start to pick them up, and you can, with enough samples, you can come up with this curve, which tells you that in the US, which is relatively populated and the time to detect fires is low, fires often burn, 50% of fires burn for about an hour before they're detected, and some fires burn even up to 12 hours before they're detected at all. And so by having early detection, we can shorten that time. And then we did some other very complicated modeling to understand, okay, if we reduce the amount of time it takes to respond to a fire, assuming that people still drive the same trucks out to a fire and it still takes 3 hours to drive over the hill to get there, how much does that extra notice buy you? And it turns out a lot. And so you can change the average size of fire in an area where you're doing active suppression by a couple orders of magnitude, though I will admit this long tail here, very large fires, is where you get the majority of acres burned. So it's not the full story, but this was extremely promising, and it led us to really lean into the FireSat project. Okay. I like this picture. What does a fire look like from space? This is the Kincaid fire in Sonoma. This fire dumped a lot of smoke into the Bay Area, which made Google executives very unhappy, and they were very excited to fund my project. So I'd like to show the picture. But this is a composite image, not in the visible. This is using SWIR bands. You can see the flame front, but you can also see a lot of smoke, and it's very hard to see fires through smoke. And when you get fires, you often get spot fires burning sort of downwind of the fire, and it's very difficult to detect that. And this is a problem with some of the imagery that we currently get today from satellites. This is that same fire. If you just limit it to the SWIR band, you can see the hot spots from the flame. Very high resolution picture. Sentinel-2, a very expensive satellite that comes over roughly weekly, so it's not super useful for early detection. Most of the fire agencies use something like VIIRS or MODIS, which gives you a much coarser picture twice a day. Here in Australia, we have Himawari, and in the United States, we have the GOES satellites for weather. And that's kind of what you see of the fire. These pictures were all taken at roughly the same time. We got very lucky and had them all kind of pass over roughly the same time. And on the right, you can see what happens when you try to take like a visible picture of the fire. All you can really see is smoke. So it would be nice to have something like the weather satellites, which take a picture every 5 or 10 minutes, but at the resolution of Sentinel-2 with maybe the bands of VIIRS that allow you to see through the smoke. Okay. And I am a physicist, so you're going to be subjected to black body curves. I apologize. And it's one interesting thing to note is that very few satellites have sort of an optimal band for detecting fire. So the VIIRS instrument does. And you can see that when you look at the Earth, I'm going to orient you. Okay. On the very left side of this graph is visible light. On the very right side is very long infrared light. And you can see the dotted line is what you would expect from a normal black body, and I won't go into the physics of that. And the sort of solid line is what you get after you go through the atmosphere. So the atmosphere absorbs a lot of light, and there's big gaps in here from greenhouse gases, and a whole separate conversation about that. But the interesting, important thing to note is that right around 4 microns, fires stand out. The Earth is black, but if you see something bright at 4 microns, it's going to be a hot fire. And so if you built a satellite around that band and it was high resolution, it should do a very good job of seeing fires. Okay, so next we tested this. We worked with the NASA folks. This is an image from an airplane test that they ran over the Creek Fire in 2020. On the left-hand side, you can see what the geostationary satellite would pick up. On the right-hand side, you can see what a 50 by 50 meter pixel would look like at 4 microns, and you get a beautiful view of the fire. So this was great. We're very happy. And that led us to this mission requirement for the FireSat project, which was we wanted to detect within 20 minutes globally a fire that's roughly the size of that like small square, which is 5 meters by 5 meters, or like the size of a classroom. And right now, what we can get from that geostationary satellite is something the size of the white square, which is about a hectare in size, before it gets picked up, because the pixels are so blocky. The fire has to be really large before you can pick it up. So that's the goal. Okay. And to do that, we're going to need to launch 50 satellites, actually 52, I believe is the number right now. 20 minutes is the peak target, 15 minutes for sort of the average temperate region where we see fires most commonly. We need it to be relatively high resolution in order to pick up fires, and we need a lot of channels. I'll explain why in a second, but the big one being the 4 micron channel. And you can see on the right, there's a bunch of satellites that exist today, and we need to be down here in this zone where we come by very often and we have relatively high resolution, and nothing really existed to look like that. This is a rendering of the actual satellite, and we did launch it. I'll get to show you pictures in a second. And then in the middle is what the eventual constellation is supposed to look like. Oh, okay. So I do have some more pictures. Okay, so on the left is our protoflight satellite, which we launched in March. Okay, and on the right you can see it. It's about the size of a mini fridge. It's about 150 kilograms in size. I don't want to tell you how much it costs. I get gray hair about it still, but it's up, and it started taking pictures. When I watched the launch, I was supposed to go in person, and then I had this commitment with my daughter to go skiing. It's a big thing. It was super fun, but I missed it. I was watching the video feed of it launching, and I was just sitting there like, please don't blow up. Please don't blow up. So many years of my life went into this. Please don't blow up. It went perfectly. It's in orbit now. We're getting pictures. Everything's in focus. I'm so happy. So this is what it looks like. This was a fire that was, or this is a picture that was taken in Northern Territories 3 weeks ago, very recently. On the left-hand side, you can see what it looks like from the geostationary satellite. And on the right-hand side, you can see what FireSat took. So this, you can really see in the mid-wave channel, the 4-micron channel, the flame front. And here in the long-wave channel, you can see some sort of residual hotspots. So the fire sort of smoldering after the thing comes through and the burn scar behind the fire. And here's another example. And this one was a lot more interesting for me as a scientist because this fire was really tiny. And we weren't sure it was a fire, but this was in the United States and people respond to fires all the time. I actually don't think that anybody really knew about this fire was occurring other than probably the people doing the cultural burn. But this one we have a lot of data on. It was really tiny, and here's what it looked like. And it was about, there was 2 of them actually about this size, and they eventually ended up burning about 1/4 of an acre in size. But we took the picture right as the fire crews were getting to the fire. So it was still very tiny in size. I was really excited to see this. But it sort of highlights the problem that we have, which is that when you see the Earth at this high of a resolution, there are so many things that can be mistaken for a fire that you have to do a really good job of filtering them out. Otherwise, you'll send people on wild goose chases. Okay. Oh, I was just getting ahead of myself. All right. When you look, this is a video of Western Australia taken 2 weeks ago. You can see fires at the bottom. These are all the channels. The way that the sensor is designed on the camera, you could picture like a square camera sensor in the back of the lens. Oh, replay that. And the left-hand side has sort of like one set of color channels. Normally when you take like a cell phone camera apart or whatever, the filter is a Bayer filter and each pixel is like slightly different color from its neighbors. We didn't do that. We took the big square sensor and we just put a piece of glass over one side that has a particular filter, and we kind of layered them next to each other. The middle one here says midwave IR is the main workhorse channel for fire detection. You can see, I apologize for the video covering it up, but you can see fires here that are coming through, and you can see what it looks like in the thermal. And having all of these extra bands allows us to reject false positives. So things like, imagine a car park and the sun gets really hot, and then if a cloud comes over, you can't see the car park anymore, but the thermal light will still go through a cloud, and it will now reflect sunlight off the top of the cloud. And so all of a sudden you have a bright, warm thing that you're looking at, and it could be a fire. And half of the Earth is covered by clouds, so there's a lot of reasons why you could have a false positive. And by having all of these channels and then throwing it into a big machine learning filter, we can drive down the false positive rate to meet our target of that 5 meter by 5 meter detection threshold. Okay. So this project did originally start at Google in my group. It was my baby. We have since graduated it to a nonprofit. So a bunch of philanthropic funders came together and kind of rescued me and rescued it. And it's called the Earth Fire Alliance. And it's partially funded by google.org and Moore Foundation and other folks. And right now, there's one satellite that's up. It was a technology demonstration mission, and so far succeeding. There will be 3 operational satellites that are currently being built out that will be live 1 year from now. And I wish there was some way to loop this. And then the next big goal after this is hourly or sub-hourly. So that'll probably be at the earliest 2027, and that's the point at which we really think that we'll see a massive benefit from early detection. And an eventual constellation is going to look like the video here. All right, so that's my last. Okay, I'm completely yanking you guys all over the place. No more about fire. Okay. Now we're going to talk about something else. This is a project that we did as sort of a joint project between Geo and Google Research. Sorry, this is a big jump from fire to rooftop solar. I apologize. So we have this product called internally called Sunroof, where we look at all of the rooftops of the world, and we try to estimate how much solar potential is on those rooftops. And we help buyers or people that are trying to install solar panels understand the value of adding a solar panel to their roof. It's like how much energy savings can they expect? How much light are they going to get over the course of the year, and so on and so forth. And okay, this is a little bit about how it works. So first we build a sort of a digital elevation model of the roof, and then we break it up into segments, and then we calculate using ray tracing how much light it gets at any given point in time. And then, oh, by the way, I see the questions in the chat. I will be happy to circle back to those at the end. And then you can kind of figure out how many panels would be economical to put on the roof, and so on and so forth. But the problem is that in order to get that high resolution digital elevation model to start with, we had to start working with very high resolution aerial data, which only covers a certain fraction of the world and only a certain fraction of the market for solar panels. And we wanted to expand beyond that. And for that, we needed to go to slightly lower resolution directly from satellite information. And that allows us to cover a large fraction of the rest of the world's population centers. And here's the problem. So we start out with a satellite picture on the left, which is relatively, I mean, by Google Maps standards, relatively low resolution, by the standards of Firesat, extremely high resolution, but everyone calls it something different. And we have this sort of pre-computed digital elevation or digital surface model, excuse me, that represents it. You can see it's not very good. And what we want instead is this. This is an actual output of the model. But what we want instead is this, where you can see the individual panels on the roof, and you can see the slopes, and from that information, and we can also orthorectify the image because often they're kind of at an angle, and from that you can calculate how many panels we can put on the roof. We can break them up into segments, and then we can do the sort of ray tracing analysis to figure out like shading from trees and all that other fun stuff. And the way it works is we take the high resolution satellite image and we run it through a SWIN transformer model. And then we have these different output heads for the different tasks that we care about, sort of predicting. We have some locations in the Earth where we have both the satellite information and the high resolution information. And so we use that as sort of a self-supervised training. And then we also sort of have the model directly predict the panel information. And then we run it through the ray tracing pipeline, and we end up with the final result. Okay. All right, let me just double check. People have been jumping on the chat, and oh man, it's about contrails and Firesat. I will circle back, I promise. Okay. How much time do we have? 20 minutes, okay. All right, second to last time, I'm gonna switch your minds. Okay, emit methane detection. This is sort of more nascent work. I like to talk about it because it's kind of fun, but it hasn't really had significant impact yet. I should mention that the reason why we did the rooftop solar thing is because we saw when we have this product in front of consumers, we can get a much higher conversion rate of people putting panels onto the roofs. We're just providing the information that they don't really have about like how much energy is it going to save them, how much is it going to cost, but it removes the uncertainty. And so we can get a significant jump in installations that wouldn't have otherwise occurred. We did a lot of retrospective analysis to figure out in markets where we have sunroof product, how much does that increase the overall adoption rate of rooftop solar? And then we look at the marginal emissions of the grid in those locations. And we also did some complicated modeling to understand like if we were driving down the odds of utility scale solar installation. But fundamentally, the purpose of that was to remove to reduce the overall fossil fuel emissions in those areas. And it's a significant number. It's a rough, number is roughly in the same order of magnitude as the contrails number, but I don't think we can talk about the exact number publicly yet. Okay. Methane. We talked about CO2, we talked about contrails. Methane is actually one of the biggest greenhouse gases. And globally, the amount of methane in the atmosphere is not well understood, actually. So we have a really hard time adding up all the numbers from what we see top down and what we see bottom up. And so figuring out where the methane is coming from has been a big challenge. In the climate community, we know that there are a lot of leaks from things like point source leaks from things like wells where we're pumping out oil or from coal mines. We also know that there's a lot of area emissions of methane, swamps essentially, or things. Actually, the classic example is rice paddy irrigation produces an enormous amount of methane. When you have a very stagnant layer of water on top of a bunch of biomass, you get anaerobic breakdown in methane production. And so we wanted to figure out a better way of quantifying methane emissions. And we started off with looking at point source plumes. So that's what I get to talk about today. And as a side note, EMIT is a hyperspectral instrument attached to the International Space Station. And so because it's a hyperspectral instrument, it can see very tiny changes in atmospheric absorption. And from that, you can back out what gases, water, CO2, methane, are in the path between the satellite and the ground. And the idea was that we could take the raw scene from EMIT, and we could sort of take a wind field and model what happens when you stick methane into the scene to pretend to inject methane plumes into the world. And so these are examples of what a synthetic plume might look like. In EMIT, you sort of say like, I'm going to pretend like I have a point source here, and I'm going to emit 100 kilograms an hour of methane. What's it going to look like? It looks like this. And then what we can do is we can figure out if our model can converge to learn to see the methane from the EMIT instrument. So on the left-hand side, you have this desert, which is actually like an oil and gas field area. You can see, and all of these are the same location, just with different labels here. So we train a model to try to detect methane, and we injected artificial methane into the scene. And this is a very low flux plume, and you can see the model doesn't pick it up, but the higher ones it does, which is great. And then this is sort of the standard method of looking at methane. We call the match filter method. It's really hard to pick up methane using a match filter, so we're trying to replace it with a more complicated machine learning model. And then this is what happens when you just look for methane in the world with this model, is you can actually see it. It's really good. So this is what you would get if you looked at the match filter. I didn't mess with the contrast. It's really that hard to see things. And this is what the model picks up, which is a really lovely thing. And here's another example, which I really like. This was an oil and gas field that had a bunch of leaks. And on the left, it's really hard to pick up using the current state-of-the-art models. And here's what we have, which I thought was really beautiful in kind of a sad way. Here's another example. This was a very high flux leak at the bottom here, maybe like 1,000 kilograms an hour, which is a lot for methane. And we do a really lovely job of picking it up, whereas you can see it's still hard to see using traditional techniques. So this is very nascent work, and the hope is that we can then we'll publish this as sort of hoping to establish it as kind of the new state-of-the-art model for detecting methane in the world. It really, with the EMIT instrument, it really only works for point source plumes. It won't work for area emissions. But there are a lot of point source plumes in the world, and with this, we hope to kind of shed light on where those are. The methane world is a bit of turmoil right now. There was a satellite called MethaneSat that launched to do a lot of this work, which unfortunately failed 2 months ago. So there's been quite a bit of sadness, and we're hoping that this kind of picks up a little bit of the slack. Okay, this is my last topic, and then I'll switch to questions. There's a bunch in the chat, and we'll take some here in the room. In the same way that we're trying to do methane accounting, we're also trying to do CO2 accounting. And the idea behind this was that there are, and this is maybe more interest for the Google people in the room, there are a lot of satellites that can produce label data for things you care about. Like in the CO2 case, OCO2 and OCO3 are custom-built satellites to detect greenhouse gases, but they only see a very tiny slice of the Earth. And we can use this as label data for other satellites when they happen to co-occur in time and space, to train to see if we can extract CO2 from, say, the geostationary satellites, even though they're really not designed to see CO2, by using the label data from the high resolution but very sparse custom sensors that were designed. So the idea here was you could basically infill the rest of the Earth. So even though you only see maybe 0.1% of the Earth with your really special instrument, you see the entire Earth with the geostationary instrument. So maybe you could do some sort of machine learning algorithm to go from one to the other. Okay, this is the second time I'm showing you guys black body curves. I'm going to skip over this really quick, except to point out that these are all the bands that the geostationary satellites have for weather, and you can see a few of them overlap with areas where carbon dioxide heavily absorbs. And so this gave us a belief that it should be possible, at least, to do this. And in fact, when you look at the imagery, you can kind of vaguely see some CO2. So we knew it was possible. It's a really difficult challenge, though, because everywhere on the Earth is slightly different, and there's clouds, and different parts of the Earth are more reflective than others. And so you don't have a highly specialized instrument. You mostly just see this in the background noise, and you don't get to see the CO2 itself. And by training a machine learning model, we're essentially training it to understand the background distribution of the Earth and remove it, so it can see just the thing that it cares about, the CO2. Okay. So the geostationary satellites sit really far out in orbit, and every once in a while, one of the OCO2 or OCO3 instruments comes by and takes a picture at the exact same time and place as the geostationary image, and this produces a bunch of training example pixels. In our case, we used 10 million of them that were co-located in time and space, and then we can train a model. So you take a series stack of the geostationary images, and you sort of take a land cover map, you pass it into a deep learning model, you give it a bunch of labels, and we just see what happens. We also, I should mention, we validated this against a holdout year just to see how good it was. This is still a work in progress, but it was, my team just gave a talk on this last week, actually, AGU, not AGU, one of the conferences. Okay. How does it do? Actually does quite well, actually. So ignore the thing on the left. This is how well it does against ground stations, but this is how well it does against the label data from the satellites. And you can see that this range here is pretty small. So 410 parts per million up to 420 parts per million. You can see the average standard error here is pretty tiny. It's just a couple ppm, which is really cool. And then here's the time series information. You can kind of see for a particular location in time how the geostationary prediction tracks the actual observations. And this is what it looks like when you create a mosaic of it. So this is the seasonal average, or the monthly average CO2 at each pixel across the Earth. And we don't really have this level of detail usually when we're looking at CO2 for the Earth. And it makes it very difficult to do things like figure out when that CO2 flux in or out of the Amazon, for example. But here we get, essentially a picture every 10 minutes. The little spots where it's kind of difficult where it's white, are areas where there's so much cloud coverage for the entire month, we just threw out the pixels. But all right, as I mentioned, this is still a work in progress. So the last thing that we did was we looked at a bunch of power plants. And I say we, this is more my team. We looked at a bunch of power plants to figure out, like, if we keep looking at a power plant, we should see a plume off of the power plant. And in fact, in many cases you do, there should be a little yellow dot in the center of each of these images to see power plants, but you can still see some that don't have them. And we think that this is because the surface reflectivity is confounding the OCO2, OCO3 labels at those locations. But I'll give you a taste for kind of the journey to make this stuff work. Okay. All right, that was my last slide. And there was a bunch of questions in the chat, and I'll start with one, and then okay, I'll do a question, and then we'll maybe go to the room. I'll do a question. Confused about the contrails and cirrus, are they the same thing or are they different? So this is a really good question. So contrails are cirrus clouds, but there are cirrus clouds that are formed anthropogenically. And then often in areas which would eventually form a cirrus cloud because the air is saturated with moisture and ready to form a cloud, but they wouldn't have otherwise occurred without a plane flying through and seeding them. Question. And if anybody in the room has questions, please just raise your hand. And I don't know if we have that. Maybe we can pass this around. All right. So. All right. There was another question from the chat, which was also around contrail formation. Why do cirrus clouds specifically generate so much extra heat? It feels like if we could somehow stop these clouds from forming through other methods, then we could reduce extra emissions. Yeah, let me actually go back to look at what the cirrus clouds look like. All right, so cirrus clouds, I mean, they fundamentally are natural. They're very high altitude clouds. So they're clouds that are formed in regions where the air is so cold that they form ice clouds instead of forming water clouds, so below zero. But because there's two things. Because they're so high up, they're below zero, so they're cold, and so they don't radiate heat into space themselves. They only trap heat really from the bottom. And that's what you see on the right. And the second thing that's interesting about them is ice is a much more powerful, it traps heat like 300 times, 200 times more effectively than water does itself. So cirrus clouds just naturally in their, because of the physics, trap enormous amounts of heat. They are a natural part of the Earth's, cloud weather ecosystem, and they do cover a large fraction of the Earth. Without cirrus clouds, we would be living in tundra here in Sydney. So they do a good job of keeping the Earth at like a good temperature, but we, by perturbing them out of, by adding extra cirrus clouds, it's just an incremental anthropogenic shift in the amount of heat trapping that we do. Another question about contrails. Reducing the impact of contrails relies on airlines changing their flying pattern, flight paths, or altitude during the flight. How willing are they at embracing this technology? It adds another constraint and potential cost. Yes, actually, that's a really great question. So if you can imagine an airline is trying to fly an optimal route for cost already. That's their job. And that includes the amount of fuel that's used, and also includes crew time and maintenance on the aircraft and all the constraints that they have to do from an air traffic control standpoint. And so they have this, what's called most airlines have a flight dispatching software that kind of creates a flight plan based on all of these constraints. And adding an extra constraint for contrails does shift the optimal flight away from what otherwise would be the cost optimum. So there is, as a result, in theory, an increase in cost for doing contrail avoidance, which might be extra fuel, or might be extra time. They can sometimes fly a little slower and save the fuel. And there's a lot of trade-offs that airlines have to do in order to make this work. So depending on where you are, airlines have different incentives. So in Europe, there's sort of like a trading standard, and these emissions are counted against, or will be counted against that. And so there's a desire to do avoidance just to meet the regulatory compliance. In other parts of the world, they're willing to do a certain amount of contrail avoidance as long as it's close to zero cost. And in fact, in a lot of cases, contrail avoidance is sort of picking between two possible paths for an airplane to fly that are otherwise kind of the same. And one path will form a contrail and one will not. And so the actual cost to the airline can be zero. And depending on how much airlines are willing to pay, they can avoid all of the contrails or 5% of the contrails or anything in between. And we've seen essentially slow adoption by the airlines, understanding what these relative cost trade-offs are, and we've done a lot of trials with them to understand that. But this is actually a main sticking point, I think, around I think they don't really want to do any extra work that they don't have to. And so part of our work here that we do is just making sure that the public is aware of the warming emissions of contrails, that regulators are aware of the warming emissions of contrails, and the airlines often are themselves not aware of this too. And so even if they have net reduction in emission targets, which most airlines do actually have that, they don't realize that they can, instead of trying to buy a much more efficient engine, they might be able to get the same impact, or maybe 100 times the same impact, by doing contrail avoidance instead. So it's a very slow moving field, but it's actually, over the last 5 years, it's gone from being something that nobody talked about to something that people are actually implementing in production. Okay, another question, not about contrails. Could the constellation of FireStats be used for any other applications? Yes, and I'm actually really curious to hear what people have suggested. One of the things that we think it could do, the obvious thing is sort of to do weather characterization. You could imagine things like extreme rainfall and flood prediction and stuff you can observe much better if you can observe the convective scale of thunderstorm formation. And you can also, with a long wave, see the change in ground temperature as rain falls down. So you can kind of get a sense for what the precipitation was based on these channels. There's another sensor on the FireSat instrument that I didn't mention, which is a GNSS receiver that sees a reflection from the ground of the satellite, the GPS signals. And from that, you can determine how much water is in the ground and how, like, the relative height. So one thing that we've talked about doing is tsunami detection in the open ocean with that, as you can measure the wave height. It's a little noisy, but as you're going over a really wide wave like a tsunami, you can kind of get the right average. And so we could potentially see those. Unfortunately, our existing satellite was clocked about 90 degrees off for this last tsunami that happened a couple of days ago. So I didn't get the data from that, but that was one of the ideas that we had. And then really it's just a question of, like, if you take a video of the Earth at a relatively high resolution every 20 minutes, like, what are you going to do with it? So there's a lot that can be done. We've talked about, besides fires, there's also a lot of enforcement stuff, like deforestation is a very rapid, is a problem in places like the Amazon. And we used to have these models that we would look at the Sentinel data, or the Landsat data actually, every week or two when the Landsat came over, and we would take a picture and we would look for the change from the previous picture to see where people were deforesting, and we would pass that information to the authorities in Brazil to try to prevent illegal deforestation. So the people doing illegal deforestation got really good at getting in and out in under 2 weeks, which is a little sad, but maybe they won't be able to do it in under 20 minutes. I don't know. Getting their lives made a little bit harder. So a lot of ideas. If you have more ideas, please send them over. Always looking for more reasons to launch more FireSat satellites. There's a question about the sunroof availability in Australia using the low-res data. I know that the team has a rollout plan for all the different geographies. I don't have the exact dates for Australia, but if you want to send me a note, I can connect you with the team that's actually responsible for that. And then, oh, thanks, Scott, for covering that. And then last question in the chat, has it been possible to compare your top-down detections for methane and CO2 against bottom-up emission reporting from the point source sites? Any surprises? For CO2, we have these TCON towers, which just measure the CO2 concentration at all these individual points. And so one of the slides does a comparison against those, and so we have the ability to do that. For methane, the story is slightly more interesting. There aren't a lot of oil and gas companies that want you quantifying their methane emissions, so they generally don't play well. This was the example for the CO2. These are ground. The orange is the ground sensor, and the blue is the satellite-derived value. For methane, it's actually a more interesting story. So there are a couple of academic groups that are doing controlled release experiments where they'll create, the most recent one is Stanford. They will go out into the field and they will release a certain amount of methane, and then they ask everybody who's trying to do methane monitoring to guess on which days they released and how much methane they released. So we're participating in those challenges, basically to validate. It's actually a blind challenge. So they do that, they don't tell anybody. And then we make our prediction, and then we send it to them, and then they'll score everybody. So we literally just sent our prediction for that last night. So we'll see how we do. Yeah. Okay. We have 2 more minutes. I don't know if anybody in the room has a question. And if not, I'm happy to stick around for a few minutes in case anyone wants to chat. All right, well, thank you, everyone. Thanks for coming. Hope this was interesting.